Hey everyone, and welcome to today's Explainer. Today's topic is, well, it's incredibly special to me. We're diving into a brand new framework that completely re-examines the BESIII X2370 Glueball observation. And full disclosure right out of the gate, the author of this paper happens to be me, Kai Huang. So today we get to explore this massive physical discovery through a radical new lens, straight from the source.
Here is our roadmap for this paradigm shift. We'll start with a quick message regarding the intent of the paper. Then review the empirical discovery of the X2370 state. From there, we'll transition into a new theory of information dynamics, look at the literal geometry of a glue ball, explore a concept called fiber bundle overlap, and end with some concrete, testable predictions.
All right, Section 1, a message from the author. Before we get into the weeds, I really want to ask you to approach this with an open mind. I want to make it crystal clear right up front that this interpretation is not based on standard quantum chromodynamics, or QCD, but it also doesn't challenge or invalidate QCD's computational power. Instead, it offers a totally complementary, geometric, conceptual language. Because this is a new theoretical framework, our focus today is going to be on understanding the true essence of glue balls purely from the perspective of information dynamics.
So, to put that shift in perspective, think about standard QCD. It focuses heavily on particle interactions, gluon gauge fields, and inputs for mixing angles. But my new Holographic Information Stiffness, or HIS-GR framework, steps out of the particle realm entirely. Instead, we're diving into geometric information dynamics, the curvature of virtual space, and fiber bundle overlaps. It's a whole new way of looking at the same underlying reality.
Let's move on to Section 2, the Xe2075 glue ball discovery.
The recent discovery by the BESIII Collaboration is an absolute landmark achievement in particle physics. They didn't just find some random blip in the data. They analyzed a staggering 10 billion JPSI events. From that, the mass of the X2370 state was measured at roughly 2395 megaelectron volts, with quantum numbers firmly established. And get this, the statistical significance exceeded 11.7 sigma. You all know that in physics, anything over 5 sigma is a definitive discovery. So at 11.7, we're looking at an undeniable physical reality.
And then there's this incredibly low suppression ratio of less than 0.081 for the K-star K-bar decay. Why does that matter? Well, it proves the particle is a flavor singlet state. When you combine that with the mass, it perfectly matches lattice QCD predictions for the lightest glue ball. And a glue ball is exactly what it sounds like. It's a particle made purely of force-carrying gluons, with absolutely no ordinary quarks inside.
Which brings us to Section 3, Virtual Space and Information Dynamics.
In the HIS-GR framework, we define something called virtual space. Now, as you conceptualize this, try not to think of a physical 3D room. Instead, picture it as a qubit state space, kind of like a Bloch sphere, that underlies all quantum-strong interactions. In this framework, glue balls aren't tiny physical spheres bouncing around. They are pure geometric excitations. They are literal information ripples on this conceptual sphere that project into our physical world as mass.
And this leads us to a really fascinating conclusion about gravity itself. In HIS-GR, the effective gravitational constant isn't just some arbitrary fundamental number. It is actually a stiffness response of virtual space to information perturbations. We are directly connecting geometry and information here. Space is literally pushing back against changes in entropy density.
Section 4, Geometry of a glue ball.
So, what happens when we apply this abstract idea to real data? At a virtual radius of approximately 0.082 femtometers, my framework directly translates that observed glue ball mass of 2395 megaelectron volts into a specific geometric curvature. We are calculating the actual geometric curvature of this information ripple in virtual space.
Think of this as a direct one-to-one dictionary translation. On the standard QCD scale, we have an energy mass of roughly 2.4 GeV. The HIS-GR scale takes that exact energy and translates it directly into a virtual space curvature radius of 0.082 femtometers. And what's truly amazing here is that this geometric scale is remarkably consistent with the standard 1 femtometer QCD confinement scale. It just fits perfectly.
Next up, Section 5, the fiber bundle overlap. Now we have to solve a major challenge. How does this pure geometry actually mix with ordinary flavor-carrying matter? To explain this, we introduce the fiber bundle overlap, or I-fiber. I know it sounds a bit dense, but it's really just a geometric metric. It quantifies how aligned the pure geometric section, our glueball, is with the flavor-carrying quark section in virtual space. Think of it like two shadows cast by the same object in different directions. We are basically measuring how nearly orthogonal or totally perpendicular they are to one another.
And notice how elegantly this unites everything. Standard QCD relies on a bunch of seemingly disconnected mechanisms, like the OZ rule and chiral suppression. But Higgs-Grants provides a single geometric origin for all of them. For instance, the well-known lattice mixing angle of 2 to 5 degrees perfectly maps onto our fiber bundle overlap, which we calculate at roughly 0.1 to 0.3. The physical phenomena are exactly the same, but now we can finally see their hidden geometric architecture.
Finally, Section 6, 2 testable future predictions.
It's time to step out of mathematical philosophy and put this to the test. Prediction 1 involves radiative decay. The strange quark phi meson has a much more compact entropy density than the omega meson. In our virtual space geometry, this compact density creates a larger separation in the fiber bundle. Because of that, we predict that radiative decay to the phi channel will be strongly suppressed compared to the omega channel. As next-generation colliders get more precise, we should absolutely see the systematic suppression driven entirely by geometry. And prediction 2 is H. Heskar's most distinctive, completely unique signature. In a vacuum, the glueball and flavor sections are nearly orthogonal, meaning they barely interact at all. But in dense nuclear matter, the local entropy density literally distorts the fiber bundle and essentially bends the information space. So we predict that the ratio of flavor-carrying to flavor-singlet decays will increase monotonically as entropy increases.
Which brings us to our final, pretty profound question. Will the next generation of colliders prove that the universe is written in the geometry of information? If these dense nuclear matter tests reveal that entropy truly bends decay ratios, it implies that at its absolute deepest level, particle physics isn't just about bouncing spheres. It's fundamentally driven by information dynamics. Thank you so much for joining me on this explainer today. Keep an open mind and never stop questioning the fundamental architecture of our reality.